In this video, we're going to use double integrals to calculate moments of inertia. So let's define what we mean by moment of inertia of an object. So an object's moment of inertia is its tendency to resist angular acceleration. So if you say this differently, if an object has a bigger moment of inertia with respect to a certain axis, then it's less likely to accelerate around that axis. So we're going to do three situations. We'll do moment of inertia about the x-axis. We'll also talk about inertia with respect to the y-axis and also moment of inertia with respect to the origin. So let's start with moment of inertia about the x-axis. The notation we're going to use is I sub x, and the formula is going to be double integral over our region of y squared delta dA. So let's draw a picture and just make sure we understand the context. So we're in the xy plane. We're talking about a region R in that xy plane. So let's say this region R. And we're measuring the tendency of this region R. Let's say it's, a flat metal plate or something like that, to resist acceleration, angular acceleration about this axis. So imagine there's rotation happening this way. Okay, so what we need to do is really look at all the different points in this region, and we want to get a sense of how far away they are from the axis. Okay, so let's imagine drawing these straight lines, shortest distance to the axis. If we're talking about distance from the x-axis, it's actually the y value that's capturing that distance. And just so that we don't care about the sign of the y value, we're going to look at this quantity y squared. Okay, so let's say this y squared somehow incorporates the distance of each point, or measures distance squared, in fact, of each point from the axis of rotation. Okay, and then delta is our density. So when I think of moment of inertia, one example that I have in my mind is just the idea of a figure skater. So really bad sketch of a figure skater. Imagine this figure skater is spinning this way. They could have either their arms outstretched like that, or they could have their arms held tightly to their chest. So let's just say that scenario there. And think about how the rotation is going to differ in each situation. So if a figure skater extends their arms out, like in this situation, that's going to slow their spin. And if they bring their arms in, then that's going to cause them to spin faster. So when we're talking about moment of inertia, or the tendency to resist angular acceleration, you have a higher moment of inertia in this situation with the outstretched arms, and you have a smaller moment of inertia in that situation there with the arms wrapped in. So essentially that's what our double integral is trying to calculate. So units then are going to be kilograms times meters squared. Let's talk about moment of inertia about the y-axis. In notation, we would call this I sub y. It's going to be the same formula as for I sub x. Just replace the y squared with an x squared then. And just something a little counterintuitive, it's more clear if we draw the picture. When you're talking about moment of inertia with respect to the y-axis, you're actually trying to measure how far away your points are from the y-axis. Specifically, you're talking about distance squared. And that distance squared from the y-axis is actually x squared. So you see the formula for I sub y has x squared in it, just like the formula for I sub x had y squared in it. And then finally, our moment of inertia about the origin. We will call this I sub 0, and that's going to be double integral over r of x squared plus y squared times delta dA. So this is really the sum of I sub x and I sub y. In a picture, you've got some region R in the xy plane, and you're calculating distance squared each of your points from the origin. And you're thinking about a rotation happening about the origin, so this way. Maybe in our previous picture for I sub y, I could have drawn the rotation as well there. So for I sub y, this is rotation about the y-axis. So that means the y values of our points are going to be constant, but the x values will be changing as this region rotates about the y-axis. And then similarly for I sub x, let's look at our picture here. So rotation about the x-axis, that means the y values of these points would be changing as the rotation happens, but the x values, the x coordinates would remain constant. So there we have our three formulas for I sub x, I sub y, and I sub 0. This I sub 0 is sometimes called the polar moment of inertia. So our problem is to find I sub x, in other words, the moment of inertia about the x-axis, for the I-beam in the picture below with delta equal k. So k is a constant here, it just means we have constant density throughout this lamina. And we've got this picture here would be part of the problem. So we've got a description of the different curves that are forming the boundary of our I-beam. So on the sides, we've got x equal plus or minus y to the fourth. And at the top and the bottom, we've got y equal plus or minus 2. So let's think about our region R. We're going to need to do a double integral over this region. So you could consider using polar coordinates, or if you wanted to do rectangular coordinates, x, y, then we need to think about whether vertical or horizontal slices would be appropriate. So I would say polar would not work particularly well here. We don't have anything like a circle or a quarter circle or anything like that. So let's stick with XY coordinates. And I would say once we decide to do XY coordinates, then horizontal slices would be the way to go. So let me just draw a rough picture of this I-beam on the side here, and we'll just convince ourselves that horizontal slices would work well. So imagine drawing a horizontal slice. See, each horizontal slice, no matter where it's positioned in the I-beam, is going to have its left endpoint on x equal negative y to the fourth, and it's going to have its right endpoint on x equal y to the fourth. So that means our x values are ranging from minus y to the fourth to positive y to the fourth. And then when we imagine scrolling through this region here, just from bottom to top, think about what y values we're capturing. Well, the y values would be ranging from negative 2 to 2. So horizontal slices will work great. And because we're doing horizontal slices, dA should be dx dy. We think about our x coordinate first and then our y coordinates. All right, so that's a description of how to actually set up our double integral. And then let's think back to our formula for a moment of inertia about the x-axis. So it's going to be the double integral over our region R of y squared delta dA. So just a quick reminder here that when you're doing moment of inertia about the x-axis, it's the distance squared to that axis that you care about, and the distance squared is actually given by the value y squared. So when you're doing I sub x, you see y squared coming up in that formula. All right, so that's what we're going to be integrating, and let's sub everything in and get our double integral set up. So double integral over r y squared times delta. Well, we're told in the problem delta was the constant k, so that can just be brought out in front, and then we're going to do dx dy since we're doing horizontal slices, and then we can actually set up the limits on our integral at this point. Okay, so x values will go on the inside integral, minus y to the fourth to y to the fourth, and y values will go on the outside integral, negative 2 to 2. And with that, we are good to go. So let's do our integration with respect to x. We'll leave our outside integral on there, outside differential on there, and we're going to integrate y squared with respect to x. So that's going to give us y squared x. And we're going to evaluate at x equal y to the fourth, and then x equal negative y to the fourth. Okay, so let's get this evaluated. K times our integral. We've still got our dy at the back. Subbing in our x values, we'd have y squared times y to the fourth. So we're subtracting off y squared times negative y to the fourth. Okay, so let's clean this up. We've got y to the sixth plus another y to the sixth gives us 2y to the sixth. So k times the integral from -2 to 2, 2y to the 6th dy, and now we're in good shape to finish this off. So we've got k times 2y to the 7 over 7, and that's going to get evaluated at 2 and -2. All right, so k times 2 to the 7, 128. If we multiply that by 2, it's 256. So 256 over 7, and then minus, this is going to be a -256 over 7. So altogether, final answer coming up, 512k over 7 for our moment of inertia about the x-axis. So remember, the higher the number here, the stronger the tendency of our region to resist angular acceleration about the x-axis. So that's a little bit of practice with calculating moments of inertia using double integrals. Thanks for watching.